Hello, thanks for joining. My name is Mohammad Farzanullah and I am a master's student at McGill University. Today I will be presenting our paper which has been accepted for presentation at the workshop at 2022 IEEE 96 Vehicular Technology Conference. The title of our paper is Reinforcement Learning Based Multi-Connectivity Resource Allocation in Factory Automation Systems. This would be the outline of our presentation. We would first start with introduction. We will then move on to system model and problem formulation. Next, we are going to discuss the reinforcement learning based resource allocation. Then we are going to discuss the illustrative results. And finally, we are going to conclude our presentation. Starting with the introduction. 5G new radio supports three main use cases, which are enhanced mobile broadband, massive machine type communications, and ultra-reliable and low-latency communication. Our focus for today is enabling URLLC in industrial automation systems. The previous generations of wireless technologies were unable to provide high reliability and low latency. However, the URLLC for industrial automation requires a reliability of 0.99999 or 5 nines with a latency of 1 millisecond. In the context of factory automation, it is observed that the devices work close to each other, due to which clusters of reliable device-to-device communications can be formed. Moving on to the multi-connectivity part. So, multi-connectivity is a promising solution to enable URLLC. And in achieving URLLC in an industrial automation system is challenging due to fading. So what multi-connectivity does is that it allows the receiver to connect to multiple transmitters in order to increase their reliability. And this is because the probability that multiple paths experience a deep fade simultaneously is lower, decreasing the probability of error and increasing the reliability. And it has been shown in literature that high data rates can be obtained by exploiting multi-connectivity. So moving on to our contributions, we focus on the mobile robot scenario, where the robots are connected to the access points to the 5G network and all the robots require control messages. We consider a factory floor setting consisting of multiple clusters, where each cluster consists of one leader and multiple members. And we divide the communication into two phases. In phase one, the APs combine the control messages of all the robots within the cluster and transmit them to the corresponding cluster leader. And moreover, the cluster leaders are able to utilize multi-connectivity to connect to multiple access points simultaneously to increase the reliability. While in phase 2, the leader receives control messages from access points and relays these messages to all members via point-to-multipoint or D2D connections. For phase 1, we adopt multi-agent deep reinforcement learning in a distributed manner for joint user association, channel assignment, and power allocation. And our numerical results show that our proposed learning-based algorithm performs close to that of the centralized algorithms and offers substantial gain over single connectivity. Moving on to the system model and problem formulation. So we consider a factory floor setting with multiple access points and multiple clusters. We assume that there is a limited set of available subbands. And as it can be seen in the figure, the highlighted part shows the cluster where each cluster has one leader and multiple members. In phase 1, each cluster leader autonomously selects the access points to connect to along with the subband and transmit power level, while in phase 2, the leader broadcasts the message to members via point-to-multipoint connection. For our simulations, we consider both large-scale and small-scale fading. Moving on to the performance metrics in phase 1. So in phase 1, we first calculate the SINR or signal to interference plus noise ratio. For the signal part, it is the summation of all the available links, or like if the cluster leader connects to multiple access points, then the summation of all of these links, while the interference is from all of the other AP to cluster leader links which are using the same subband for transmission. And then using the Shannon capacity formula, we can use the SINR to calculate the rate, where over here W shows the bandwidth of each subband. Similarly, for phase 2, we can also write down the SINR, and in the case phase 2, the interference would be from the other cluster leader to member links which are using the same subband. And similarly, we can use the SANR to calculate the rate for each of the cluster member. So moving on to the problem formulation, each robot is required to receive the cluster's control messages of size B within the time constraint of T. And so we can formulate the requirement as the probability of successful delivery of packet having size B, and like these equations shows this for both phase 1 and phase 2. So for our resource allocation problem in phase 1, we need to find for each cluster leader the set of serving access points, the subband, and the power level in order to maximize the packet delivery probability. And to achieve this, we use the multi-agent reinforcement learning approach. While for phase 2, we consider a scheme where each cluster leader transmits to its cluster member on different time frequency resources. Moving on to the reinforcement learning based resource allocation. So in our approach, each cluster leader acts as an agent and interacts with the unknown environment. Based on the reward it receives, it refines a strategy for power allocation. In order to ensure collaboration, we use a common reward for all of the agents during the centralized training stage. Moreover, the testing is implemented in a distributed manner where the trained deep network is used to select the action. And for the reinforcement learning, there are three main elements, which are the state space, the action space, and the reward. So moving on to the state space. So for the state space, consider the measurements from the last time step, which includes the channels from the access point to the cluster leader, the interference at the agent, along with the remaining payload and time. The action space, meanwhile, consists of the access points selected, the occupied subband, and the power level control. For simplicity, we limit the connection of each cluster leader to 2 access points. And in case if the cluster leader connects to 2 access points, it will be assigned the same subband. Moving on to the reward design, we use a common reward for all of the agents to ensure collaboration. This reward is given by the sum rate of all cluster leaders at time t. And moreover, as you can see, for a given cluster leader, if it has completed transmission, its rate is denoted as U, which is greater than the maximum rate possible. This is to indicate successful transmission of the packet to the agent. So the reinforcement learning algorithm we use is the deep Q learning. In reinforcement learning, the goal of the agent is to maximize the cumulative return, which is the sum of the reward at the current and future time steps. Meanwhile, a policy is a function that maps the state to action. The Q value gives the expected return of a state action pair with a given policy. And so the aim is to find the policy that maximizes the return at each time step. So in Q learning, if you can accurately estimate the Q values, the optimal policy would be to take the actions in each state that maximizes the Q value. However, due to practical reasons, deep Q learning is used, which uses a neural network as a function approximator for the Q values. The deep Q network takes the state as the input and outputs the Q value of each action. This slide basically shows our training algorithm and testing strategy. So we consider an episodic setting with each episode corresponding to the time limit of delivering the packet. Each episode consists of multiple time steps. At the start of each episode, the device location and large-scale fitting is updated, while at each time step, the small-scale fitting is updated. At each time step, each of the agent observes its local channel and takes an action. Based on it, it receives an reward and moves on to a subsequent state. This tuple of state action reward state is stored in the memory and it is used to train the deep Q network. Meanwhile, in the testing phase, each agent uses its trained DQN to take the optimal action in phase 1. Meanwhile, as described earlier, a fixed scheme is used for phase 2. Moving on to the illustrative results. So for a simulation setting, we consider a square factory floor with a size of 40 by 40 meters square, where the robots can move around with a velocity of 1 meter per second. And the cluster members are located close to the cluster leader, and the cluster moves together to complete a specific task. For the path loss, we consider the A1 indoor scenario of the winner to channel model. And meanwhile, for we consider long normal shadowing with a standard deviation of 3 dB. Also, we model small scale fading as Rayleigh fading. This slide shows the simulation parameters and the DQN implementation. So some of the important simulation parameters are that there are 4 access points, and we vary the number of clusters between 4 to 8. There are 4 members in each clusters, and we discretize the transmission power of access point into 4 levels, that is 30, 25, 20, and minus 100 dBm. We vary the payload size of the robot between 20 to 100 bytes. For the DQN implementation, the neural network we use consisted of 3 hidden layers with 83, 41, and 20 neurons respectively. And we use Rayleigh activation function with a learning rate of 0.001. And so we developed 5 benchmarks for comparison. The first was random allocation. The second is centralized algorithm, where each cluster leader connects to the nearest access point and exhaustively searches for the subband and power level that maximizes the sum rate. Then there is single connectivity MARL, where we use reinforcement learning with the restriction that each cluster leader can connect to just one access point. Then there is greedy single connectivity, where each cluster leader connects to the best available link at maximum transmit power, and greedy multi-connectivity, where each cluster leader connects to the 2 best links available to transmit at maximum power. So over here, we compare our performance with while we vary the payload size for 4 clusters. And over here, it can be seen that the payload delivery probability uh, our proposed algorithm achieves a payload delivery probability of 1 for up to payload size of 60 bytes, and it achieves more than 0.999 for up to 100 bytes, and outperforms both the centralized algorithm and single connectivity MARL. Another interesting point is that for the greedy algorithm, which is a naive strategy, the single connectivity performs better than the uh, than the multi-connectivity, and this is because due to higher interference when all of the cluster leaders attempt to use multiple links to complete their transmission. However, for reinforcement learning, the uh, multi-connectivity performs better than single connectivity, which shows that multi-connectivity can yield a greater benefit only with an intelligent resource allocation design. Also, we observe the performance while we vary the number of clusters, and it can be observed that when the number of clusters are 6 or less, we achieve a payload delivery probability of more than 0.995 for both 40 bytes and 60 bytes. However, the performance degrades when we increase the number of clusters to more than 6, and this is because of the increasing interference amongst the cluster leaders, and also it becomes difficult to train when we increase the number of agents. Moving on to the conclusion, so we develop a distributed resource allocation algorithm based on multi-agent reinforcement learning in an industrial automation system with multiple clusters, and we use centralized training and distributed implementation, where where the action taken is based solely on the local channel information at each agent, and it can be seen that the multi-connectivity approach performs better than both the single connectivity and centralized algorithm. And the main key takeaway from the presentation is that enabling multi-connectivity offers substantial gain in reliability. So moving on, these are the references. Thank you for listening to the presentation, and have a nice day. Bye.